Let's take a look at translational equilibrium. Translational equilibrium sounds kind of complicated, but the equilibrium part simply means balanced forces, as in Newton's first law, where we have balanced forces. That is, we're saying that the net force must be zero. And if we have a net force of zero, then the velocity has to be constant. And that velocity being constant, that's our translational part. So let's say we've got an object here. It could have 500 forces. But if we know it's moving at constant velocity, then the vector sum of all those forces has to be zero. In my little example here, I've got a free body diagram here. There's 4 forces acting on our object. We're going to assume our object is either at rest or moving with constant velocity. If that's true, then I should be able to add these 4 forces, meaning join them head to tail. And if I do so, join them all head to tail, I should end up in a situation like this. So when the vectors come around, join back up again like this, that means that our vector sum is equal to 0. And that means our net force, our resultant force, is 0. So if you understand what translational equilibrium means, you're going to easily be able to answer this IB question. Pause the video, try this question, come back for the answer. Hopefully you said right away that the resultant force has to be 0 newtons. And why is that? Because of this statement here. It's constant speed or constant velocity. In other words, we've got this box here, Q. It's moving with constant velocity. If it's moving with constant velocity, F net is 0. It's got to be. Here's a second IB question. Based on exactly the same principle, this comes up over and over again on IB exams. Pause the video, try the question, come back for the answer. Hopefully the first thing you noticed was they're moving at constant speed or constant velocity, and that means that the net force has to be the same. In fact, it has to be a net force of 0. Now, of course, the weight of this bigger mass is going to be bigger. And if we're going to have 0 net force in both cases, the resistive force is going to have to be bigger for the bigger mass. And that means the correct answer here is B. Let's try a third example. In this case, a lawnmower is being pushed with a force of 50 newtons. And we want to find out the force of friction and the normal force on the lawnmower, assuming it's moving with constant speed. And just to simplify things a bit, let's take G equal to 10 newtons per kilograms instead of 9.8. So as always, let's start with a free body diagram. First thing, we're going to have a push force along the direction of the handle here. So we're going to have a push force in this direction, and it's going to have to be 50 newtons directed at 30 degrees. And then, of course, every object on Earth has a weight vector, mg, and mg will be 100 newtons, being as we have a 10 kilogram mass. We're going to have some friction opposing the motion. We'll label that F. And then we're going to have a normal force coming up this way from the ground onto the lawnmower. So those are the 4 forces acting on this object. Now, what you want to notice here is one of the forces isn't like the other. You'll notice that the normal force, the weight, and the friction, they're all acting vertically or horizontally. But this one here is acting at an angle. So it's a little bit different. And what we're going to do is we're going to break it down into components. Because if we do that, we can replace that force by the components. And if we do that, we should get exactly the same action. Our lawnmower should move in exactly the same way. The lawnmower wouldn't know the difference if it was pulled with a 50 Newton force or if it was pulled with a force component like so and another force component like so. Now we just need to work out what those components are. This component here, it's adjacent to the 30-degree angle, so it's going to be a cosine of 30 degrees, multiplied by the hypotenuse, which is 50. If you work that out, you should get an answer of 43.3 newtons. And over here, this side, this component, is opposite 30 degrees, so it's going to be a sine of 30 degrees times the hypotenuse, which is 50. Multiply that out, and you get 25 newtons. So what we're effectively going to do is kind of wipe out this vector. We kind of pretend it's not there. And replace it by these purple vectors, the components. So remember that vertical and horizontal are independent of each other. So what we're going to do is look at the vertical stuff first. This is my little symbol for indicating we're going to look at the vertical stuff. So vertically, we've got a normal force that's upwards, and then we've got this 25 newtons that's downwards, and we've also got 100 newtons that's downwards. And overall, the size of the up forces has to be just as big as the down forces. That is, the magnitude of our normal force has to be equal to 100 plus 25. In other words, our normal force is going to be 125 newtons. So now we've got the normal force. Let's go on and look at the horizontal forces. Once again, the horizontal forces are independent of the vertical, so it's a totally separate problem. Now, there's got to be no overall horizontal force. So if I look at the stuff to the left and I looked at the stuff to the right, they should equal each other. The magnitude of the left forces should be equal to the magnitude of the right forces, which is to say, the force of friction should be equal to 43.3 newtons. So we found our force of friction and we found our normal force. The key idea is to use components, so all of your forces are effectively vertical or horizontal. Here's another example. We've got some strings attached to a weight here, and we're best off kind of imagining that we've got a ring here, so that the string is attached to the ring here, and here, and here. And then we've got an equilibrium situation. What I want you to do is see if you can work out what the three tensions are. And you can take G equal to 10 newtons per kilogram, just to simplify your math. So pause the video, try the question, come back for the answer. So hopefully you started off trying to find T3, because if I do a free body diagram for my 10 kilogram mass, well, the weight is straight down at 100 newtons. And the only other force that's acting is that T3. And that means that the size of T3 has to be equal to 100 newtons. And then the second step is to take T1 and break it up into components. So these components would be T1 sine 45 and T1 cos 45. And then the next step is to consider the vertical and the horizontal stuff separately. So for the vertical stuff, all the up stuff has to equal all the down stuff. That is to say, what's up? Well, it's T1 sine 45 degrees. And what's down is T3, which is 100 newtons. So that means T1 is going to be equal to 100 divided by the sine of 45, which should give an answer of about 140 newtons for T1. Now we can work on T2 by considering the right and left forces, the right and left stuff. To the right, we've got T2, and the size of T2 is going to have to equal T1 cos 45. But of course, now we know T1 is 140 newtons. And if you multiply that out, you should get back the 100 newtons that you started with. So T2 will be 100 newtons. T1 is going to be 140 newtons. And T3 is going to be 100 newtons. Here's an example involving a force table. If you haven't used a force table before, what you have is a ring with strings attached to it. And each one of those strings passes over a pulley, and then there's weights creating tension in the string. And also on the table, there are angles here, so you can figure out the angle of orientation of each one of your forces. So what you do is you alter the angles and the weights until you get that ring just sitting there in equilibrium, such that the ring is exactly centered about the center of the table. And usually there's a peg in the center of the table. So if I put a little more weight on here, the ring will move and it won't be centered anymore. So I've got an equilibrium situation, and it has to be such that each one of these strings would kind of pass through the very center of the table here. Now, it might be a little hard to read the values on here. It's 500 Newton weight, creating 500 newtons of tension in this string. This is a 250 Newton weight, and this here is a 310 Newton weight. And the angles here, a little bit hard to see. This one would be 40 degrees. This one is 90 degrees. These are the polar angles. And this one here is 314 degrees. let me call this first force here, I'll call that F1. This will be F2. And this one will be F3. So we're going to try to figure out what is this mystery force over here such that they're in balance. So what I'm going to do is add up F1, F2, and F3. Find the resultant of those three. That's going to give me a vector pointing in this direction that has to be equal and opposite to this hidden vector. And that's going to allow me to calculate the hidden vector. So I'm just going to add up my three forces, F1, F2, F3. Of course, it's much easier to do that in Cartesian component form, so let's convert the three vectors into Cartesian component form. My F1 is going to be equal to the magnitude of that force, 500, times the cos of the angle, the polar angle, 90 degrees. And then the y component is 500 sine 90 degrees. So of course I'm going to get 0, 500 for my force F1. F2, once again, magnitude of F2 is 250, so it's going to be 250 cos 40 degrees, 250 sine 40 degrees. Multiply that out. My F2 is going to be the vector 192, 161. And then F3, same procedure, 310 cos 314 degrees, 310 sine 314 degrees. So my F3 vector in Cartesian component form is 215 and then negative 233. So now what I'm going to do is get F resultant, FR, just by adding up the components here. So 0 plus 192 plus 215, that's 407. And 500 plus 161 minus 233 is 438. So that's my resultant vector. That would be the x component and the y component of the resultant. So what I can now do is figure out what my resultant is in magnitude. I want to convert back to polar form. And it's going to be 407 squared. It's just Pythagorean theorem, plus 438 squared, all square rooted. Take that square root and you should get 598 newtons. Then you can figure out the angle. It's going to be the inverse tan of 438, the y component, divided by the x component, 407. The x component is positive, and that means that we don't need to add 180 degrees to our answer, and the correct answer there would be 47 degrees. So my mystery vector should just be the opposite of this vector. So my mystery vector should be equal to 598 newtons at 47 degrees plus 180 degrees. Remember, add 180 degrees to get the opposite vector. So that's really 598 newtons at 227 degrees. So let's check out our answer. A little bit hard to read, but what it says here is 600 newtons, and the angle here seems to be approximately 225 degrees. So we are a little bit off because we were making estimates in reading the angles. But in the end, we did figure out what our mystery force has to be. So what I want you to get out of this video is that if you've got any object and it's moving at a constant velocity, and that constant velocity might be 0, then you know that the net force, the sum of the forces, the net force, or called the resultant force, has to be equal to 0. So then what you can do is break the forces up into components, horizontal and vertical, so that you're effectively looking at nothing but horizontal and vertical forces. And then what you do is you set all the up forces equal in magnitude to the down forces, and set all the left forces equal in magnitude to the right forces. And in most cases, that's going to enable you to solve what you're looking for. And that's all for today, folks. Thank you very much.